everyone, my name is Preeti, pursuing my education in Sri Venkateshwara College of Engineering, Bangalore. Today, let us learn about volume integral and Gauss divergence theorem. So here is the content, volume integral and Gauss divergence theorem. Let us learn about volume integral. In mathematics, particularly multivariable calculus, a volume integral, triple integral refers to a integral over a three-dimensional domain. It is a special case of multiple integrals. A volume integrals are specifically important in physics for many applications, for example, to calculate flux density or to calculate mass from the corresponding density functions. For example, integrating the equation of f of x comma y comma z is equal to 1 over the unit cube, else the following result. Triple integration of 0 raised to 1 into dx into dy into dz is equal to integration of 1 comma 0 and integration of 1 comma 0 is of 1 minus 0. So the value integral of the unit cube is 1 as the expected. This is a rather trivial, however, and the value integral is a far more powerful. For the intents, if we have a scalar density function on the unit cube, then the value integral will be given the total mass of the cube for the density function. So here f is to r cube raised to r and f is to r of z comma y comma x raised to x plus y plus z. Let us learn about applications. The application of integrals to the computations of area in the plane can be extended to the computations of the certain values in a space, namely those of the solids of a revolutions. A solid of the revolutions arise from revolving the region below the graph of the function f or f of x about the x or y axis of the applications. Let us learn about Gauss divergence theorem. In the vector calculus, the divergence theorem is known as a Gauss theorem, and the theorem which relates the flux of a vector field through the closed surface to the divergence of the field is in the volume enclosed more preciously. The divergence theorem states that the surface integrals of the vector field over the closed surface, which is called the flux through the surface, is equal to the volume integrals of the divergence over the region inside the surface. Initially, it states that the sum of the all source of the field is a region which, since regarding a negative source, gives the flux out of the region. The divergence theorem is an important result for the mathematics of a physics and engineering, particularly in electronics, statistics and flux dynamics. In these fields, it is usually applied in these dynamics. However, it generally to any number of dimensions. In one dimension, it is equivalent to the integrations of a part. In two dimensions, it is equivalent to the Green's theorem. Explanation using liquid flow. Vector fields are the often insulated using the examples of the vector fields of the fluid, such as a gas or liquid. A moving liquid has a velocity of a speed and the direction at each point, which can be represented by the vector, so that the velocity of the liquid at any moments form the vector field. Consider as an imaginary closed surface as inside the body of the liquid, enclosing the volume of the liquid. The flux of the liquid out of the volume of any time is equal to the volume rates of fluid crossing this surface. That is, the surface integrals of the velocity over the surface. Since liquids are incompressible, the amount of liquid inside the closed surface volume is constant. If there are no source or sinks inside the volume, then the flux of the liquid out of S is 0. If the liquid is moving, if many flows into the volume at the same points on the surface S and the out of the volume of the other point, but the amount of flowing in the equal, so the net flux of a liquid out of the volume is in a liquid flows. However, if a source of liquid is inside the closed surface, such as a pipe through which liquid is introduced, the additional liquid which pressure on the surrounding liquid causes a outward flow in all direction. This will causes a next outward flow through the surface S. The flux onwards through S equals to the volume rate of the flow of the fluid into a S from the pipes. Similarly, if there are a sink or a drain inside S, such as a pipe which drains the liquid off, the external pressure of the liquid will be cause a velocity throughout the liquid direct inwards towards the location of the drain. The volume rates of the flow of the liquid inwards through the surface S is equals the rate of a liquid removed from the sink. If there are a multiple sources and sink of a liquid inside S, the flux through the surface can be calculated by adding the volume integrals by the source and subtracting the rate of the liquid to the sink. In Gauss diversion theorem, the volume of rate of the flow of the liquid through a source or sink with the flow through a sink given a negative sign. It is equal to the divergence of the velocity field at the pipe mouth. So integrating the diversion of the liquid throughout the volume enclosed by S equals the volume rate of the flux through S. This is the diversion theorem. The diversion theorem is employed in any convergence law which states the total volume of the sinks and the causes that is the volume integrals of the divergence to the net flow axis of the volumes. Applications. The diversion theorems has many uses in physics and engineering. In a particular, the divergence theorem is used in a field of a partially differentiation equation to derive equation modeling heat flows and conservation of mass. We use the theorem to calculate flux integrals and electrostatic fields. So this is about a volume integral and Gauss divergence theorem. Thank you.